Here we have a constant speed buggy set up on a table. Directly behind the buggy is a sonar connected to my computer through a LabQuest. I'm going to turn the cart on and collect position and time data from the sonar as the car moves across the table. Here's the real-time data being collected by the sonar. The sonar only collects distance and time data, but Logger Pro assumes I am doing a kinematics project and automatically calculates and displays the real-time speeds and acceleration data as well. These graphs should look familiar to you from your own buggy lab. The position graph shows a diagonal line implying a constant speed. That constant speed is showing up on the velocity graph. Since the velocity graph is flat, the acceleration graph is 0 during the motion. Instead of using the sonar, which gives very rough data, let's use the motion capture feature that we used in the gravity demonstration. In this video, I'm tracking the silver hubcap on the front wheel because it's easy to see. Every time I click the mouse, the computer draws a blue dot marking where the hubcap was and then advances a frame. This is a tedious process. It took me just over 5 minutes in real time to mark up the 3 seconds of video, but I'm speeding up the playback so you won't get bored. Notice how evenly spaced the blue dots are. With every dot drawn, the spreadsheet in Logger Pro writes down the x and y coordinate of the dot and the timestamp as well. Here's the graph of the position of the cart as a function of time. That's a pretty straight line, as we would expect. I'm going to insert a second graph. On the y-axis, I'll ask the computer to display the speed of the buggy. I'm going to shrink both graphs so they can both be seen, and I'm going to line them up so that they share the same time axis. I can put a linear fit on the position graph and get the slope, which represents the speed of the buggy. The graph indicates that the speed is about 0.42 meters per second. Now look at the velocity graph. The data is a little rough looking, but that's because we are zoomed in so close. In the first few instants, we can see the speed increases, but then it is constant for the rest of the time. Notice that this constant speed is just over 0.4 meters per second, just like the other graph suggested. Let's spend some more time with the velocity graph. The slope of this graph represents the acceleration of the buggy. Here's what the acceleration graph would look like. But that's not all. The area of the velocity graph is also meaningful. It represents the distance that the buggy went. Even though this is not exactly a nicely shaped graph, the computer can calculate the area under the graph easily. It says that the buggy went 1.7 meters. If we check with the position graph, we can see that this also says the buggy went 1.7 meters. Let's try this process again with the fan cart. First, we'll use the sonar to record the motion of the cart. You can see the pattern in the graphs is a little rough. The sonar is a little too sensitive to the spinning of the fan blades to give a nice picture. We can get a clearer picture with manual motion capture. I filmed the cart and imported it into Logger Pro. Again, I set up a coordinate system and began taking data. I followed the front edge of the cart this time. Notice what is going on with the data points. They start out really close together, but spread out as time goes on. Remember, each blue dot happens 1/30th of a second apart. This means that the cart is moving slowly at first and then gets faster. Let's look at the graph of the data. Notice the shape, it looks like a parabola. Remember that the slopes on this graph represent the speed of the cart. The initial slope is 0, and as time goes on, the slope goes up, and so does the speed. Let's shrink down the position graph to make room for a velocity graph. This graph is linear. The speed of the cart is increasing at a constant rate. The slope of this graph is the acceleration of the cart. The linear fit for the data indicates that the acceleration is 0.22 meters per second each second. Lastly, we can look at the area of the velocity graph and get the distance that the cart traveled. This technique suggests that the cart moved 2 meters. Once again, this is in agreement with the distance shown on the position graph.